So, hello everyone. So, welcome this round of PF5. So, first of all, I would like to introduce the member of the jury to everyone. So, I am Jiang Fujun from Taishidae. We also have Guan Xisheng 教授 from Taiwan 大学 and Wen Bingyi 教授 from 中正大学 Zhang Ziwei 教授 from Taiwan 大学 and Cai Shangfang 教授 from Taiwan 大学 So next, so please the captain of each team, please introduce your member to everyone. Let's start with the reporter, then opponent, and finally the reviewer.
And hello everyone, we are Team ECN 1917 and we are from National Zhonghua Girls Senior High. And I'm Zhen Ziqing, Chen Luyin, Tu Rilin, Dang Yunyu, and Dai Huiyu. Thank you.
Hello everyone, we're Team Newgate from Kaohsiung Girls Senior High School. I'm Maggie Liu, this is Evangeline, this is Peggy, this is Jenna, and this is Olga.
Greetings, honorable judges and worthy opponents. We're Team Weige Erze from Taipei Weige Senior High School, and starting from we have Yang Chenxian, Liao Junrui, Zheng Naiying, Zhang Naixing, and Cai Renji. Thank you.
Okay, so the next is the preparation of a reporter. You have 5 minutes. So also each presenter, please write down your name on the black form. droplet reporter, you can begin your
Okay,
presentation.
so hello everyone, I'm Tori from Team ECN 1917, and today I'm going to report to you problem number 1, fractal fingers. Here's the problem statement. The effect of fractal fingering can be observed if the droplets of an alcohol mixture is deposited onto diluted acrylic paints. How are the geometry and dynamics of the fingers influenced by relevant parameters? And we will mainly focus on the process of the droplet fractal and the evolution of the size of fingers. And here's our experiment video. We can see that it will first expand the inner circle radius and then expand the fingers. Okay. And here's the process of it to fractal. So first we just dilute an alcohol, isopropyl alcohol on the acrylic paint, and because of gravity, it will be like thinner, and it will expand the inner circle radius, and here it will expand the fingers. So for the energy of it, for this part, the potential energy decreases, the thickness decrease, and surface energy increase, and the kinetic energy increase. But for here, since it will evaporate, and we test the temperature of it, we can see that it's decreased, so that it will take away some energy. And here, because of there is a viscous force, the kinetic energy will decrease. And here's, we think that our pattern is very similar to the pattern that sedimentary instability occurs. That it occurs in the porous media or halogen, which is between two plastic plates, and when the less viscous fluid placed on the more viscous fluid. But in our experiment, our two surfaces, one is the acrylic paint, one is the air. So we don't, and also the sedimentary instability occurs because of the pressure between the two plastic plates. So we don't think that it can be used in our experiment. So here, theory of dimension. So for a line, the dimension of it is 1. For a surface, a flat, the dimension of it is 2. But for fractal, it is between 1 and 2. And how we calculate it, we use box counting dimension. So for this, NV test is the number of grids that occupied by fingers, and for the S is the length of a grid. So here's our formula that we calculate the dimension of it. So when S is very close to 0, we can ignore this so that we can get the dB in our experiment. And here we use imagery to calculate it. And here's theory of diffusion. Since they're both, so diluted acrylic paint and the isopropyl alcohol, they're both a kind of hydrophilic, and they're mixed together, and we can see that after an hour, there is no divided into 2 layers, so they will mix. So here we can use the Stokes-Einstein equation to explain it. So the diffusion coefficient will relate to the dynamic viscosity of it. And here's Rangel effect. We want to explain why the droplet expands. So after it evaporates, like the surface tension of water is bigger than isopropyl alcohol. And here, after it evaporates, since the edge is thinner and the edge at the center is like thicker. So after it evaporates, the proportion of water here will be higher and surface tension will be higher. And here the surface tension will be lower, so that it will produce a surface tension gradient. So it causes Marangoni pressure, and it is proportional to the velocity of the droplet. Here is theory of inhibition of Marangoni effect. We want to test if the evaporation is a main result that causes this kind of phenomena. So we put our experiment in a container, and we just spread some isopropyl alcohol in it to reach a saturated vapor pressure, which the isopropyl alcohol won't evaporate. And here we can see that there is no fragmentation, but there is a little wave at the edge. So yeah. So we would like to explain why the droplet becomes fractal. So because as I just mentioned, at the edge it will be a little wave, and it will wave, and the Marangoni force will try to expand the radius, and it will cause curvature difference. And here is the curvature of different part. So curvature difference will cause different pressure difference, and pressure difference will cause that the droplet try to fractal. And here is theory of surface tension. So we use Young's equation. So for gamma 1 is surface tension between outlet pan and the air. Gamma 2 is between that surface tension and the gamma 2 is surface tension between the air and the alcohol. And here the part we didn't calculate is because they just mixed together. And for gamma 1 is bigger than gamma 2, it will expand, and when gamma 1 equal to gamma 2, it will just stop right there. And theory about pressure, and for this part, magnetic force, and this part will be the viscous force. And since it keeps evaporating, the magnetic force will decrease by time. And when it's equal to viscous force, it will just stop right there. Okay, and here's our model we found at the paper. So they got four formula: magnetic effect velocity, expand time, conservation of evaporation, conservation of volume of water. We can deduce the two formula. And later we would like to investigate the relationship between the initial concentration minus the critical concentration and the viscosity and the time and the maximum inner circle radius. So here our setup, we use pipette to control every volume of the droplet, and we got heating plate to control the temperature. And here we use isopropyl alcohol. It's because the critical temperature for it to evaporate is lower, so that we can do the experiment easier. Okay. So for the definition, this is the radius of finger, and this is the radius inner circle radius. When the outer circle radius, this is the outer circle radius, this is inner circle radius. And outer circle radius minus inner circle radius will be the radius of a finger. And here is the width of a finger. So for parameter 1, we change the concentration of isopropyl alcohol mixture. And we can start with too low concentration. It won't fractal into like regular fingers. So here we choose this one to be our critical concentration. And we can set in this place when the concentration increase, the fingers width. The fingers will quite remain the same, but the inner circle will be bigger. And for discussion of the finger, since at first the magnetic force, is bigger, and then the viscous force equal to magnetic force, so they will just simply stop. And here we can see that with concentration increase, the radius will be bigger, and the maximum intercircle radius will be bigger, and the time consumed will also be bigger, which is because like with more concentration, they'll need more time to evaporate. And the surface tension gradient will be bigger, so that magnetic force will be bigger, so that the radius will be bigger. Here is discussion about the inner circle radius with and time consumed with the concentration. And we take log of all the data. We can see that the slope of the inner circle radius is 0.25, which quite match similar their proportion to a quarter. And here the slope of it is very close to 0.5, and which quite match our theory. And here is discussion of finger. We can see that outer circle radius minus inner circle radius will be our finger length, and the finger's length will quite be the same, but the time consumed will be different. Okay. And the width of finger and the dimension of finger, they just both remain quite the same, since the velocity of the viscosity of the aquapan is quite the same. And here, parameter 2, we change the viscosity of duality aquapans. And here, we can see that with too much viscous, the force of it is too big that the fingers will just can't expand. But for this situation, for the surface of the aquapan isn't smooth, so we won't calculate it. And for this, since they just mix together, so it won't produce fingers. And we can see that with this range, with less viscous, the finger will be bigger. And here is a discussion about radius. We can see that with more viscous, the time consumed will be longer, and the radius will be maximum circle radius will be shorter. Since more viscous, it will expand slower, and the magnetic force becomes smaller, so the radius will be smaller. But here, it won't quite match the theory since we have to consider the diffusion of it, which is related to the viscosity. And here is the discussion of finger. Outer circle radius minus inner circle radius will be our finger's length. And we think that the tendency of it just quite remain the same, but just the time will be different. And here is the discussion of viscosity of different concentration of acrylic paints. So here we can see that the concentration increase, the weight of it will decrease since when there is like too much force, it will be like thinner. But for the dimension of the fractal fingers, when the concentration here increase, the dimension will increase since like when it becomes thinner, the curvature, like the curvature will be like more curvature difference will be like obvious, so like it will just extend like more fingers so that the dimension of it will be bigger. Here's our conclusion. So first, diffusion and magnetic effect will cause the fractal of the fingers. And for the experimental part, when the concentration of isopropyl alcohol increase, time consumed increase, inner circle radius increase, and the rate of finger increase. Weight and dimension of the finger remain the same. And for changing the viscosity of acrylic paint, with an increase, the time consumed increase, inner circle radius decrease, rate of finger remain the same, and weight of finger increase, dimension decrease. Thank you for your attention.
Okay, so the questions are opposed to the reporter and the answers of the reporter.
So the first question is, in your video that you show, why are there fingers that form?
What do you mean?
Why does not it spread in circular, instead it has fingers?
Since that there are curvature difference between in the liquids, the curvature difference will cause the liquid wants to extend in different ways, and it is kind of random.
Okay. So the second question, how do you make sure that all liquid is dropped at one time since you use a pipette and instead of a stream?
I mean, we have to use pipettes to control the volume of it, and we just press a little bit faster to make sure that it will just spread out in one time.
Then that means you add a pressure to the droplet? Because you press it very fast at one time, right?
But we just make sure that distance between the pipette and the surface is quite just 0.5 cm, so the pressure won't be that big to affect our experiment.
I mean that there's still a velocity that's caused by the pressure you add to the droplet. So do you think that it will affect your experiment results?
Maybe yes, but it won't affect that much.
Okay. So the next question is, what do you think are the most important parameters?
You mean affect the inner circle radius or the fingers?
The fingers.
The fingers will be viscosity.
Viscosity. Okay. And I guess that's it. Thank you.
Okay, the preparation of the opponent, you have 3 minutes. corner, please. Take all.
Dear judges, reporter and reviewer, my name is Evangeline from KGHS Newgate, and today I'm talking about fractal fingers. So first is the problem statement. The effect of fractal fingering can be observed if a droplet of ink and an ink alcohol mixture is deposited onto diluted acrylic paint. So the problem told us to investigate how the geometry and dynamics of the finger influenced by relevant parameters. And the reporter just said that their main point is the process of droplet fractal and the evolution of fingers. And here's a summary of the reporter. First, they talk about their theory. Is the diffusion and is Stokes-Einstein equation. And the second one is Macaroni effect curvature. And third one is surface tension. And about their experimental factors, they talked about concentration. And the conclusion is that Macaroni force causes this phenomenon. And also, when concentration changes, inner circle's radius changes. Here are some pros and cons about the reporter. First is that they have a clear presentation, and second is that they have a detailed theory and has a good explanation about it. Third is that they add error bars to their graph. Fourth is that they compare their experiments with their theory. And areas for improvement is that there are more parameters could be considered, and we will talk about this later. And here's some of the points that we would like to discuss with the reporter later. The first one is about the theory. We would like to talk about the formation, the purpose, and the limitations. And about the experiments, we would like to talk about the control and parameters. So can the reporter please? Okay, we can just start because I have the questions. So, what purpose does the ink serve?
I mean, what purpose?
Does the ink serve? Like, which part does it play in this phenomenon?
I mean, insert
The ink.
the ink.
The ink you added.
Ink just want us to we can clearly see the phenomenon. Like we add the purple one.
Yes. And what about the alcohol?
Alcohol, and since it will keep evaporating, it will cause Marangoni force that cause the droplet to expand.
Okay. And another question is, the fingers appear in two phases. Can you explain this?
You mean,
Like, there will be some main fingers, the big ones, and then they will have small fingers. Can you explain this? Can you understand, or I can draw a picture? So like when the finger goes out, like if here's a droplet, you'll first have a circle, and then it will have a main stream like this. Then it will have small fingers. So can you explain this phenomenon?
we think that first the width of it will become thicker, and then as every time it's just fractal, it will be a little bit smaller. Maybe just a half. The width of it will be a half smaller, and then just when every time it's just fractal,
Yes,
the width of it will be
why?
smaller.
Why?
We think that it might be because of the curvature difference. So first the curvature here will be like this, and then it's just fractal, like the curvature difference, and then it's just fractal, and here maybe for this part the curvature difference isn't that obvious, so maybe just a little bit, so that the width of it just will be a little
So it will keep going.
yeah.
Yes. circumstances can the two fluids start to finger? Under what circumstances?
I believe that when it reaches the maximum inner circular radius.
Okay. So for example, if you change your acrylic paint to another fluid, will the phenomenon still occur?
Acrylic paint, if it changes to something like hydrophobic, the fragment won't be like this. If we change to hydrophobic, like maybe it will be like into like little droplets. But here, it can just diffuse with our acrylic paint, so that for this our experiment, it can just the alcohol can mix with the dilute acrylic paint, so it will be fractal. But if they cannot mix with each other, maybe the phenomenon would be like little droplets.
Yes. Okay, and then the next question is that you mentioned at some concentrations there are no fingers, and why?
Concentration of alcohol or the acrylic paint.
Acrylic paint.
Okay.
Do you want to put it?
Okay. You mean like this part?
Yes.
We believe that they just like mix together too much. Yeah. Since that we did the research about here, and there's also no like the
This one is because you said that the fingers are due to the evaporation of the alcohol. But I'm asking that why in some concentration of acrylic paints the fingers can't be observed.
Maybe they just like mix together like this. They just mix together like this, and yeah, so that the fingers won't just produce.
Can you say it again?
They just mix together like. Yeah.
Okay. Then the next question first. So you mentioned that gravity affects the droplet. Is it?
Yeah.
Then how would the height dropped from affect your experience?
We think that if it is too high, when it is too high, the gravitational potential energy is converted to like shear stress. Like when it will change to shear stress, so that the velocity of it will be higher. So the inner circular radius may be, or the speed of the droplet may be like faster.
So did you do an experiment?
No, we just
You just have a guess.
Yeah.
Okay. And so how do you control your height? Because you said that you put the pipette at 0.5 centimeters. So how?
Use the ruler to
a ruler beside the. And the next question is, since that gravity would affect the results, then how do you make sure that your acrylic paint is totally smooth?
We think we just place it in the area for a long time, and maybe it would just be like smooth.
Then if the water, like if you put for a long time, then if water inside the acrylic paint evaporates, then it will change your concentration.
We think be like the long time isn't like you mean that lasts long. Maybe just like 10 or 5 minutes, and the water won't just evaporate as much, since the speed of water isn't that fast.
So you think that putting 5 minutes can make it totally smooth?
Yeah, and we have to mix the acrylic paint and the water like uniform, so that maybe the surface will be smooth. Yeah, we think better.
Okay, so like from this picture, do you think there is a height dropped from that cannot form fingers? Like, is there a limit?
Limits? You mean?
Like from which height, if you put the pipette, then you drop down the droplet, you can't see.
We think maybe no. Maybe there will be no limitation.
No limitation, but you said that if the height is too high, then it will convert into shear stress.
I mean for shear stress, I mean that when the gravitational potential energy will change to the force that right there, right in the horizontal place. So the velocity of the droplet will just be faster.
Okay. And what will happen if you have multiple drops of ink at once?
You mean like many droplets in?
Yes, like because if you have, okay, I'll draw a picture. Like if you have like this,
Yeah.
and you have one drop over here and another drop over here, what do you think would happen?
I think maybe there's still fractals, but there'll be some kind of age right there since it is here it wants to fractal, but here it also wants to fractal. So here will be like eight, kind of eight. Yeah.
So you said that you drop the droplet very fast, right? Like with some pressure. And how can you make sure that it doesn't have multiple droplets?
We just drop it like we place the pipette like very close to our pencil, and we just make sure that it is just in one place. And since if there will be like two places, we won't calculate the data. The experiment will be just crazy.
So does the initial area of your droplet affect your results?
Initial area
Yes.
of the droplet. Initial volume of the droplet.
Yes.
I think maybe yes, because with like more in our theory here, this will be the volume of the initial volume of the droplets. So we think that yes, it will affect the results.
Okay. So you said, do you think the fingers, like when it fractals, is it from the surface or from inside the acrylic?
We think that maybe it's from the surface.
From surface, then, like, I mean, if you drop the droplet very fast, then it makes an smooth surface.
Oh, you mean?
Yes.
We think that maybe it just has a little bit like inside the acrylic, like a little inside the acrylic. Since the acrylic is a little bit hydrophobic, it won't just be like so deep in the acrylic. So like maybe we just consider the surface.
But you said that you have to put at about 5 minutes to make it smooth. And 5 minutes you make it smooth, and when you put the droplet, do you think that it will have a hole inside it?
A hole?
Yes, like it's not, okay, never mind, next question. If the volume is the same, but when you drop it has different initial area, will this change your results?
Which initial area? You mean the volume or?
So when the volume is fixed, the initial area is different.
Initial area, you mean different place of the particle
Time's up.
Yes.
Okay, time's up.
Like this. Oh, okay. Thank you.
So the opponent, please summarize the discussion.
So about the formation. About the formation, we had a great discussion about it. And about the purpose, we found out that the reporter has a relation about between its theory and its experiments. And about the limitations, we talked about its experimental equipment, and we found out that if they use a pipette and just press it at a very fast speed, then it would affect its results. And about the experiment, like I just said there, if they press it at very fast speed, then it would affect the results, and that means that they didn't really control all the variables. And next is that their parameters, like the reporter just talked about in their report. And that's it. Thank you.
Okay, so question of the reviewer to the reporter and the opponent, and answer to these questions.
For both the opponent and the reporter, can a droplet deposit on the paint break down into tiny droplets? Just like the picture you drew there.
With acrylic paints, like no.
No.
Okay. You told that when the fingers start to form, and they have a maximum radius, and what's the radius?
The inner circle radius.
You have
The maximum inner circle radius.
You have a quantitative number or some
No.
okay. For the experiment, do you measure your, and you say you place the acrylic paint a time to make it flat, and do you measure the drying out time and the viscosity of the paint, the relation?
Well, no, we didn't do it.
Okay. So both for the opponent and the reporter, do you think that the finger formation is random or not? And if not, please explain why.
Well, we think that it's random, since that if different place the temperature will be like a little different, since like if fluid is
Okay, thank you.
Yes, it is random.
Okay. So, you say that you measure the width of the finger, but the fingers, every finger's width is not the same. So how do you measure it?
Measure like the different, like every fingers, and take average of it.
So, do you measure? Do you count that there have the clusters of the fingers, or how do you define it is a finger?
Oh, I mean, between the finger there will be a distance.
Yes.
Yeah, and kind of like every distance there will be a fingers.
So what's the distances?
Depends on like every different.
So every fingers is the distance between the fingers is not the same due to the
different
concentration.
Yeah.
Okay. And how do you define a finger?
I agree with the reporter.
Okay. So both for opponent and reporter, how do you think that the change of the thickness of the acrylic paint will affect the patterns?
Patterns.
The fingers formation?
No.
Okay. And so do you have any equation about the height of your pipette and between the velocity?
Okay, time's up.
Thank you.
So preparation of a reviewer, 2 minutes. Okay, reviewer, please take the floor.
Honorable judges and worthy competitors, I'm the reviewer from Uyghur Day. And today I'm going to present problem number 1, fractal fingers. Our focus is to explain the phenomenon and investigate the relevant parameters. And the phenomenon of the reporter is that the radius increases and forms the fractal fingers. And then theory considering dimension, diffusion, Marconi effect, and the viscosity force. And their experiment is about diluted acrylic paint and an ink alcohol mixture. And the part about reporter is their experimental results were presented in the animated skits and numerous pictures. Theory presented in detail, and the graphs were drawn to support the theoretical model. And the counts are no clear experimental setup was shown, and no definition of the terms were present, and failed to provide how to measure and define a fractal finger, and failed to further elaborate on the equations, lack of parameters, and failed to prove that the theory matches with the experimental results. And the pros of opponents is that some short, concise, and on-point questions that directly point out the flaws. And cons are that lack of understanding in the reporter's presentation, focus on too much irrelevant details, provide no personal insights nor suggestions, and ask several questions that are extremely out of scope. And the first discussion is that different velocity caused by not controlled drop height. And the reporter says it doesn't matter, but the reviewer's opinion is that it will influence the rate of fractal dispersion, but not the results. Like the velocity, the circle expands, but it will not affect the fingers, dimension, or the length. And the discussion 2 is concentration of the acrylic paint. And reporter says ink alcohol and acrylic paint mixed together. And will height influence the results? And the reporter said that they control the height. And our opinion is that different height will influence the velocity, but not the finger's length or the radius. And my question is that can a droplet deposit on the paint break down into tiny droplets in any concentration or and our opinion is no. And how to define the maximum radius that when the fingers start to form? And the reporter say very ambiguous, and they didn't provide a number. And we change in the thickness. And for instance, it's 0.01 centimeter. What will the thickness influence the pattern of the fingers? And we think that the density of the fractal fingers will increase. And the paint drying out time, and I think the reporter needs to control it, because it will influence the length and the viscosity of the paint. And the point is that they lack of quantitation of the data, and the inadequate measurement of the data, errors exist, were not considered, and chemical structure of the different ink alcohol mixture effect on experiment. Thank you.
Concluding remark.
Okay, so first, thank you the opponent and the reviewer. So for the reviewer, we have just for the setup we have just mark out that which the characteristic of the pipette and equipment and all the other things, and we do match our theory with our results, since we have like take log of it and just and definition of a fractal. We have just talk about the dimension of it. And for the remark for why in high concentration of the equipment or fractal, it is because that with the liquid mixed together, and we will have diffusion, so we do not see the fingers. And for the opponent, perhaps they can discuss the parameter we have drawn, such as the concentration of isopropyl alcohol and the viscosity of the acrylic paint, and how we analyze it without theory and formula, since both diffusion and evaporation will be the key point to affect the result of the experiment. So let me just just conclude my report again. So first, diffusion and Marangoni effect will cause the fractal in the liquid. And here, when the viscosity of acrylic paints increase, time consumed increase, inertial correlates decrease, weight of the finger increase, dimension decrease, and when the concentration of isopropyl alcohol increase, time consumed increase, inertial correlates increase, weight of finger increase, and weight of the dimension of finger will remain the same. And this is all of my remarks. Thank you.
Okay, so any questions from the jury?
I like the reporter's experiment that you show no evaporation and no fingers. Right? I also noticed that in your equation you have the code evaporation constant. So my question is, if I have drop it like this, the evaporation constant will be here. It will be the same here and or here. Will be different here and or the same in the finger and the droplet. Evaporation constant.
Oh,
Do you think about that?
Since the evaporation just occurs in the surface of it, so and when at here,
in the finger and the droplet.
Here the width, the area of the fingers will be smaller. So maybe, I mean, here and here, the area here is bigger and here is smaller. So.
I mean, in your equation, you have an evaporation constant.
You mean where? On the evaporation constant. You mean here?
The previous one.
Here.
Yeah. You have evaporation constant, the last one.
Oh, evaporation constant.
Yeah. Do you think that will be the same as like
Yeah,
here and
it
here?
will be the same.
It will be the same. What do you think, opponent?
Yes, it would be the same.
I think it will due to a difference in concentration.
Any further question?
Yeah, could we come back to the first answer you gave in your summary, the concentration? You say for high concentration of pen, it won't fractal because they will have diffusion.
I kind of just it's a little wrong. This for high concentration, that there will be diffusion, and it is with low concentration of the acrylic paint, it will diffuse. Yes.
You should be able to explain it using your theory, right? That the concentration comes as one of the factors. Can't you use any of your theoretical formulas to tell us why that? Maybe it takes longer time that you don't observe it, or maybe because it's just a small effect. But you are saying that it won't happen. Where in your theory deal with this aspect?
Maybe that's because the time consumed of it is too small.
No, I mean use your theories. And then give me explanation now. We were not interested in the.
If the time is too small, they won't have that much time to fractal. I mean,
in relation to the concentration question,
concentration.
Where does it show up that it won't crack? We were not testing your understanding. We were just asking that you correlate your theory with these experimental findings. Is it in there or is it not?
No, it's not.
Okay.
No, it's not. Okay.
So if there's no any question from the jury, so scoring time. Alright, so the scores for the reporter. Seven, 8, 7, 9, and 8. Scores for the opponent. 7, 7, 6, 7, and 6. Score for the reviewer. 7, 7, 7, 7, and 7. Alright, so let's take a 15 minutes break. Jonathan, do you want to start now?
Yes.
Okay.
Dear judges, opponent, and reviewer, my name is Evangeline, and I'm from KGHS Newgate. Today, I'm discussing about problem 12, rise kettlebells. This is the outline of our presentation. So first, the problem statement is take a vessel and pour some granular material into it. For example, rice. If you dip e.g. a spoon into it, then at a certain depth of immersion, you can lift the vessel and contents by holding the spoon. So the problem statement told us to explain this phenomenon and explore the relevant parameters of the system. During my presentation and experiments, I would mainly focus on the relationship between the tested friction and different variables, which are filler, cavity, and stick. So first is the observation. Like we had a video over here, and so when you put a stick inside the bottle filled with something like rice, then you can take up the whole thing, and let's see a video. Like this, when you put it in, and the rice would fit up every space inside the vessel, and then you can lift the whole thing up. Yes, just like this. And here is our theory and equation. So first, when the F is the force that you lift up the stick, equals to mg, which is the weight of the whole system, and gravity, and then you can lift up the whole thing. And F also equals the Fs max plus the mcg, and mc is the mass of the stick, and g is gravity. And Fs is the friction between the rice or filler that we put inside the vessel. And they have a mu-s, and it's mu-s and n, which is the pressure between the stick and the rice and the vessel. And also, actually, the rice, when you put some pressure inside it, the rice changes its shape. And if you calculate it with K, then you can get the n, which we have over here. And also, we are going to define two parameters. One is A, alpha, which alpha equals the area of the actual area that has contact, the rice contact with the stick. And AC is the actual area that the stick has. And this is the first ratio number that we have, which is alpha. And the second is the field ratio, which is beta. And beta equals the amount of rice inside it, and also it's how much what is the height and the amount of rice it has. So by beta we can know how compact the rice or the filler that we put inside this. And from this equation we can know n from here, and furthermore we can know Fs max and get back to this equation and find out the maximum F and mg, which equals mg, and we can know that by how much can what is the biggest mass that we can pick up with this structure. And next is the parameters that we are going to explore. First is the filler, first is the size of the filler and different surface of the filler. Next is the cavity. We will let the cavity have different friction, and also we will experience when the cavity has different radius, what will happen. And third is the stick. We will put the stick in different depth and see how will it affect the results. And also we will have different sticks with different radius and see how it would affect the results. So first, this is our experimental equipment. We have a vessel over here, and then we have a stick which we put in. On the stick, we will put a marker here, and we can control how deep the stick is inside the vessel, which has rice or filler. And next is that we have a string on top of it. And the way that we calculate how much is Fs max with how much is friction is that we put in this we put the stick inside to the vessel, and then we have a spring up here, and we can calculate that how much force we actually use to get the stick out of this vessel, and so we can know that how much friction it actually has and the maximum friction that this system would give. And next is our results for our experiments. And first is that we put red bean, green bean, rice, and millet inside our vessel and see how it affects the results. The result is that red bean has, here's a little bit of stick. The red bean will have the smallest friction, and green bean in second, rice in third, and millet at fourth. So millet can pick up the biggest mass. But however, then we found out that actually using different kinds of beans, we will have different surface, which in our theory and equation we consider would affect our results. Therefore, we did further investigation about this. Then we bought two kinds of rice, which is long glutinous rice and brown glutinous rice. It has the same kind of surface, however, its size is different. And I show it over here. One is 0.3 centimeter, and the other one is 0.8 centimeter. After experiment, we found out that the brown glutinous rice would pick up bigger mass, which means that it has a bigger friction and then the long glutinous rice. And this actually proves that the first equation of our theory. And the second experiment is that we put different filler inside the vessel, and instead of changing the size, this time we changed the different surface of the filler. We used purple rice, long brown rice, and long glutinous rice. Actually, purple rice, then we calculated how much friction coefficient it has, and purple rice has the smallest friction coefficient, and second is long rice, which is almost equals to long brown rice, and the biggest one is long glutinous rice. And after our experiment, we found out that long glutinous rice can pick up needs the biggest force to get the stick out of the bottle, which means that it can pick up the biggest mass of the whole system, and also means that it would have the biggest friction. Our third experiment is that we have different radius of the tube, so that we can, we have different radius of the tube, which is 2.8 centimeter, 4.5 centimeter, 5.6 centimeter, and 7.2 centimeter. After calculating, we found out that 2.8 centimeter needs the biggest force to get the stick out of the vessel, and like I just mentioned before, which means that it can pick up the biggest mass of the system. And we consider that this may because of friction transfer, and which means that when the vessel is over here and the rice is over here, it has to transfer the friction from here to the stick. And if this length is too long, then sometimes it can't transfer that much friction, so it would affect our results. And the next experiment is the different depth, which was mentioned above from the beginning, is that have different contact area, and we did 10 centimeter, 15 centimeter, and 20 centimeter of the depth. And the result is that with deeper, when we put the stick deeper, then we can have we can test a bigger friction, and which also again means that we can pick up a higher mass of the system. And next we did different radius of the stick, and just like the depth experiment, we found out that with bigger contact area, with bigger radius, then we can have a bigger contact area, and we can pick up a bigger mass of the system. And next is the different contact area. We put some sandpaper outside the tube, from like the inner part of the tube, and then we put rice inside it. Because like I just said, the rice gives the stick friction, and the rice gets friction from the vessel. So we want to know that how the friction, the mu_s from the outside of the vessel would affect our results. So we changed the mu_s of the outside, which is 240 cW, 180 cW, 80 cW, and also 80 cW has the biggest mu_s. So this result proves that with bigger friction outside in the inner side of the vessel, then we can pick up a bigger mass of the whole system. And here comes to our conclusion. First is the parameters. We found out that the size of the filler would increase our main mass. And second is that the maximum friction of the filler would increase the mass that we can pick up, and also the contact area of the stick and the filler. The decreased parameters is the radius of the tube, which I mentioned that if the length is too long, then it can't transfer that much friction to the middle of the stick. And next, here is a review about how our equations and our experiments are related. First is that this equation, we found out that with different surface and different filler, we will have different μs, and which proves that this equation is related to our experiments. And the second one is a different size of the filler, then we can know that with different contact area ratio and different fill ratio would also affect our experiments. And the third one is the sum of the friction. With different depth, then we will have different amount of contact area, and with different radius of the stick, we will also have different contact area, and this would affect the sum of the friction and also the total friction that we have, which would, like I just said from the beginning, affect how much force that we need to get the stick out of the vessel, and which also equals to how much mass that we can pick up with the stick. And that's the end of my presentation. Thank you.
The question of the reporter and answers of the reporter. 2 minutes.
Can you turn to page 4? Can you play your video? Okay, we can discuss about it direct. First of all, is your stick sharp?
Yes.
Then in your model, is it sharp?
Yes, but we only use the sharp stick. You mean like,
Then is your theory the same as your experiment?
Yes, it's the same. Like
but is it sharp?
Yes, but the one that we use to calculate the different depth and the different.
In your model, is the density of the rice, is the density in the upper part and the downward part same?
Actually, we just press it multiple times and like as hard as we can and make sure that it's all the same.
Okay, then do you think the closer part of, do you think the rice closer to the stick and further to the stick, are the density the same? In your opinion, or in your experiment, is it the same?
Yes.
So you consider it the same. Okay, then if you shake it, well, the density may be more average, because I think if you stick it in, the rice closer to the stick may be higher. Have you considered that?
No, like I just said, when we put in the stick, I know that the density would change. So we will actually push as hard as we can to make sure that the whole density is almost the same.
So the rice that, the stick was pushed into the can, but the rice that was there was pushed aside. Then maybe the rice, the density of the rice has become higher.
Yes, so we push again to make sure that it's almost the same for every area.
And do you consider your static friction is the maximum?
Actually, we repeated the whole experiment every time.
Yes or no question?
No.
So you didn't calculate the maximum friction?
We can't assure that it's the maximum, but after 20 times
up.
of
Thank you.
Preparation of the opponent, 3 minutes. Okay, opponent, please take the floor.
Good evening, worthy opponents and honorable judges. Today I'm going to pose about problem 2 of rice kettlebells. So the problem statement, we take a vessel and some granular material in it. For example, rice. And we dip a spoon or maybe a stick into it, and we test the lift. We test how we can lift the vessel. And we mainly focus on the parameters and how we explain this phenomenon. And in their phenomenon, they used a single rod to pick up a certain mass of rice and the can. And in the theory, they talked about friction and the gravitational force. And in the experiment, they considered multiple parameters, yet the model drawn does not really fit into the actual experiment. And the pros and cons of the report. First, about the pros. They have clear definitions of terms in the initial part of their presentation. And their data was presented in clear graphs. And there are various parameters they considered and they conducted experiment about. And the cons. The graph of the experimental setup exists everywhere, which is kind of different from their experiment. And the mathematical equations they mentioned in their theory was not really concluded in their data they presented. And they kind of failed to explain why the specific parameters were chosen. And they failed to include the trend lines. And they simply used bar graphs, then we kind of cannot see how the trend goes. And please, report. First, I want to continue to discuss about the maximum static friction. Do you consider in your experiment, is it maximum?
In our experiment, we repeated every experiment for 20 times, yes, and take out the 4 maximum one and had the average. We can't say that it would be maximum for sure, but we can say that if we don't have the data after 20 times of experiments, then there's a too low possibility of getting it.
Can you consider that all 20 of them are not maximum? So are they maximum eventually?
We can't consider, we don't know if it's actually maximum, but we can say that if we did 20 times and we didn't get a bigger data, then we can consider it's very close to the maximum data.
Okay, so you find the biggest data of all.
Yes.
Is that correct? Okay. Then, in my opinion, I think if you have the maximum friction, static friction, then the moment you lift it, it will fall down. Is that correct?
Actually, we stabilize the vessel on the table and lift up the stick. So it doesn't change when we lift up the whole thing.
The moment you lift it, when it has an acceleration, I think the moment it has acceleration, when it's over the maximum static friction, I think it falls down because it turns into connected friction. Is that correct?
It doesn't fall down. Oh, you mean that when we take out it?
Yeah.
Actually, we have a video and find out that because the graph of friction is like this, so we are finding this point.
Yeah, sure.
Yeah, so we had a video and find out that how much we can calculate the maximum amount.
Can we go to that point? So I think you mentioned this one, right?
Yes.
Yes.
So finding this point.
Yes.
And we set a roller over here, and we put our vessel over here, and our spring over here. So when we will see the video in slow motion and find out how the maximum data from here, so we would know it's this point instead of this point.
Okay, but in my opinion, if you lift it up with an acceleration, I think the maximum static friction you measure is maybe here, or maybe here. It may be close to the maximum, but it cannot be the maximum, right?
But if it's not at this point, then it won't move. Because if it didn't get over this point, then it won't have the movement friction.
Okay, thank you. The next part, I want to talk about the surface. This right. I want to talk about the surface of the rice. Do you consider that in every kind of rice, the surface, the material of the surface is the same?
Can you say it in another way?
Do you consider this value the same in every rice?
No. Not every piece, but if it's the same kind of rice, it will be very, very, very close.
Yeah, sure. But did you consider that in your experiment?
Oh,
That there may be
this
different values,
amount?
yeah?
Yes. In this picture, when we consider the different surface, we actually tested the mu by how much that it was like that.
Okay. So do you consider that? Let me draw your model, please. This is your model, right? Yeah, right. Do you consider that the stick is totally attached to the rice without any space?
I mean that the rice would have this, like this, and it will have space over here. So we had another equation over here. This one.
Okay. Then
Yes.
do you consider it totally attached to the stick?
Like mostly attached, but there still be spaces. So we have this equation that tells how much their space is
Okay.
between it.
And in your experiment, when you attach your stick into your model, does the surface of your rice, does it go up?
Yes, it goes up. But when we change the variables, we make sure that every experiment we do all the height is the same. Like which means the density is actually the same.
So the density change. So the density doesn't change before and after you stick your stick.
Yes.
Go.
It goes up, but it doesn't change because we push it back.
You push it back.
Push
Can
the
you
rice
elaborate
back.
on the push back?
Like I mean, if we put it like this, right, and if we want 15, like maybe 17 centimeters of the rice over here, and we would first put in like this much, and we put inside the stick, then it would go up, maybe it goes here, it would push it back to here. And when we have like rice, red bean, green bean, then all the height is the same.
Oh, but I thought you stick a stick into it. Then the
Yes.
volume of the rice is actually smaller because you need to get this away, right?
Yes, but we make sure that the contact area is the same.
Okay, then again, in my opinion, I think the density of the whole rice isn't the same. Do you agree?
I think it's the same.
But in your experiment, when you attach it into it, the rice here, that was here, was pushed to the other sides, right?
Yes.
Then do you think that the density here is bigger than here?
So we push it to make sure that the whole system has the same density. Because we push it, so
You push it, then-
I know what you're talking about. You said that because if some of the rice goes from here, so here should have a bigger density than here.
Yeah,
But it
sure.
doesn't have. So we push it down, and that
And-
the
okay.
whole density is the same.
Let's say, if this area has a bigger density, and this one has a smaller, if you give a pressure here, and make both of the volume become smaller, do you think the density of them become the same?
So first, here is big and here is small in the same vessel doesn't commonly appear. So actually, you mean like when you put inside the stick, but when you put inside the stick, it actually has a whole round of density that has increased it. So if we push down, then we can actually just put these rice to here and make the whole density the same.
Well, in my opinion, I think there are still differences in them, but okay, this is Ian. And can you elaborate on how the friction transfer? I think you used the verb transfer. Can you elaborate on it?
Like, wait, I need to say something. Is that first, if the volume is same, when we put like different rice and different time, when the volume is same, then it means that the density is same. When we have the same rate. Do you agree with me?
Yes.
Okay, and so to your question is from here, when we have the rice here, like if you have rice over here and we have the stick over here. So first, if we have F here, and this one to go up, so the rice will give its friction down. And so if the rice is going up, then this will give its another friction. Yeah, so this friction goes from here to here. This is transfer.
Oh, so you mean, I don't think it is transferred, I think it's just, yeah, okay.
It's actually this friction equals to this friction.
Okay. Have you considered that if you're putting your stick in the center part of your can?
Yes, like we use, I didn't show over
Yeah,
there, I didn't say over there, actually we have a cap here and
what?
a cap
Okay.
over here, and we have, we calculate it like this,
Yes.
so we will put inside the stick every time at the same time in the middle of it.
Okay, thank you.
And also this one is, I just said it, it's not transfer, it's that the first rice causes the second rice friction and the second rice causes the third, and until it's over to the stick.
Okay, and now do you consider that every friction that is existing in this model, do you consider every of them in the same direction? Or maybe it's the opposite? Do they point at the same direction?
They point at the, you have to see which object you are considering.
Okay, let's talk about every rice.
Every rice, then, but when the whole rice is over here, then yes, it has the same.
So I read about the theory that when you have let's just draw two balls here, and when the ball is dropped down here, this ball tends to go up because it was pushed, right? So it has a friction that points downwards. Is that correct? And when this ball tends to go down, it has a friction that tends to go up. Do you think this phenomenon exists in your model?
No, because your balls are moving. Like
Your balls are moving? Your rice?
Yeah, the rice didn't move, so it's actually not safe from the.
But I think your rice sort of moves, right? And when you press it, it moves. When you
It
your
moves,
stick
but
into
when we
it moves.
calculate the friction or the F, it doesn't move.
Can't this be a static friction? I think it can.
Well, I don't.
You don't think so? So this
You
can't be
mean
a
that
static friction? When I push it down here and these three balls don't move, can it be static friction?
yes.
Then do you consider that friction can point at the opposite direction?
It has to see which object you're actually considering.
Yeah, so in my opinion, I think in your model there can be different directions of your friction. Okay, I think that's it.
Thank you.
Okay, so the opponent summarize the discussion. 1 minute.
Okay, first I would like to appreciate my reporter. Oh, okay, so first of all, the pink region is the critical condition. Okay, so we first discussed about the theory I mentioned, and he thought, the reporter thinks that the density of the whole vessel is of the rice is a constant in the vessel, but I don't think so. And I think the part that is closer to the stick, the density may be higher. And I don't think there exists boundary condition for their model, and I think they failed to consider olfaction in the theoretical model. First, for instance, the theory I mentioned, and they failed to include the trend line in bar graphs, and they failed to perform exact experiments according to their theoretical models. Thank you.
Okay, so question of reviewer to the reporter and the opponent.
Okay, so first for the reporter, did you control the velocity that you just lift up the vessel? Yes. And do you?
Oh, you mean the velocity that you pick the stick up or the whole thing up?
Like the whole thing.
We didn't pick the whole thing up. We
Like,
actually
just the
stabilized
stick, just the stick.
just the stick.
Yes.
We control the
Okay,
velocity.
and how do you measure the friction force since you don't have the device picture in your report?
We use a string.
And in your video, the way that the direction you lift up isn't vertical. Do you think that will affect? Do you think
That video is only for observation to explain the statement.
Do you think that if it is not vertical, it will affect?
Of course, you will.
So, yes. So you do think that it will affect?
That one is for observation.
Okay. So do you think that if it is not vertical, it will affect?
Yes.
And for your stick, it is short. So do you think that will affect the result?
In our theory, we didn't consider if the stick is sharp or not. So it won't affect our theory and our results as long as we use the same stick.
And do you think that if it is short, will that affect the result?
Yes, because the angle of the static friction will change.
Thank you. Do you think that the pressure in your experiment is important? Pressure, like vertical pressure? Yeah.
Yes.
Yes. Do you think it is important?
Can you elaborate on what kind of pressure?
Like
Pressure.
the pressure between the okay, thank you. That's it. So you think that at every place the density of rice is different?
I think it is. Yes, I think it is different.
And do you think that in different places the density of rice is different?
In general, no.
So do you think that when you put a stick on the center and at the edge of the vessel, will that change the result?
We didn't consider that in our experiment, but we control. Yes, it would affect. So we control every time we put it in the middle.
Okay. And
I don't think their method can control it as a constant, but yes.
So and you think that the maximum friction coefficient should be the moment that it's just falls down, right?
Because when it goes, when it has an acceleration, and the thing turns into.
Okay, time's up. So preparation of review of 2 minutes. Oh, okay, so the reviewer, please take the floor.
Okay. Hello everyone, I'm Tori from Team ECN 1917, and today I'm going to review to you problem number 12, rice kettlebells. And here's the problem statement. We think that it will be mainly focused on studying the force analysis for different systems and explain how does the depth, static friction coefficient, and the radius of the stick affect the maximum static friction force. An overview of the reporter for phenomenon, and I just did up the stick, but yeah. And for the theory, they got solid effect and resultant force equal 0, and the energy and the maximum static friction normal force. And for experiment, they changed the size of filter and cavity and the stick. For conclusion, when they get the stick out, the red bean will bigger than green bean, bigger than rice, bigger than millet, and they're both round shaped. And the maximum friction of the filter and the contact area of stick and the filter increase. The maximum static friction increase for radius of the tube, it will decrease. And overview of the reporter, abundant parameter tube have a fully observation on this topic, and well theory illustration, and do lots of times of the experiments. But for cons, didn't clearly explain the phenomenon like how the station of rises will be when lifting up, and the control variable is not accurate enough, and didn't talk about how the density change when pouring the rice into a container, and the definition of maximum of static friction coefficient to each other isn't clear. Overview of the opponent. So to summary, they discuss the definition of the maximum of the static friction conflicts and the consideration of in every place of the vessel the density should be different, and for pause, well discussion of how the density affects the lifting force, and point out the missing point of the limitation for lifting of the vessel. But for pause, didn't point out the limitation for lifting out the for discussion, the opponent asks, do you consider the material of the surface? Opponents say, just one of the parameters. We think that if we change the material of the vessel, the friction coefficient of land will be different, and then affect the force to lift up the rice, and also for testing the maximum static friction. For second question, opponent asks, have you considered about how the density affects the lifting force? Reporters say yes to control the height of it. We think that the density of the rice should be considered, since it will affect the condition when the rice will lift. What's more, when pouring the rice, the bottom pressure of the container will also increase, so it should also be considered. And for third question, opponent asks, how do you test the maximum of static friction? And reporter said, put it on the fact table and then the reviewer agreed with the report. So for missing points, for reporter lack of the investigation in rice density, since rice density in the container affects the normal force and the friction between the rice and vessel, and then cause the rice could be lifted or not. For opponent, they didn't give their own opinion about the model to the reporter's point, and didn't point out the limitation of the depth, since it also be a factor in performance parameters. And they agree that pressure is important, but they didn't discuss about it. And thank you for your attention.
Okay, the concluding remarks of the reporter.
So first, the material was poured in chute to make sure that the density was as even as possible. Pressed, then the stick was put in and it was pressed again, so that we make sure in general the density is the same. And second, we did not lift the whole vessel up. We actually just fixed it on the table and pull out the stick. And the third one is that the red bean has a smaller friction than green bean, than rice, than millet, which will have some errors in our picture. And the fourth one is that we noticed there were 2 parameters changed in our first experiment, so we did the second and third experiments. And last is that we control the height of the rod and had in contact with the rest. And next is that the variables. First increase is the size of the filler, the maximum friction of the filler, and the contact area of the stick and the filler. The decreased variables are the radius of the tube. And that's my conclusion. Thank you.
Okay, any question from the jury?
I have a question for all you three. First of all, to the reporter, do you think friction is the only force that holds us with that vessel?
It's the only force that we experiment.
What do you think?
I think the gravitational force and the friction affects the whole experiment, and the friction holds the vessel.
Yeah, I just and also there are normal force in the experiment, and also the pressure between the vessel and the rice.
So my question is, if you cook your rice and you did an experiment again, do you still think friction is the only force that holds the vessel?
No, it becomes because the viscosity changes.
Viscosity change. So this is viscous force. So
It changes the friction.
it changes. Still friction.
It changes the viscous force.
Huh? Still friction, but change the friction.
It causes a viscous force.
Cause viscous force, but still friction.
Friction is still considered, but has other things that makes it up.
Okay. What do you think?
I think it causes the tension, and the viscous force makes the thing thicker and becomes easier to lift up.
What do you think?
It will be not particles, it will be just like the fluid, so it will be like similar to rigid body, so that the contact area will change.
Still friction.
Still will also be a factor.
Still friction.
Viscous force only exists in fluid, right? When it's in motion. Even static fluid doesn't have viscous force. That's the main property, key property of fluid. If it's static, there's no viscous force. So in your situation, viscous force shouldn't matter, right?
But it's wet on the outside, and also
No, it's not moving. The fluid is not moving.
I think when the cooked rice is, when there is
Your point, I got it, so you don't have to. Adhesion is If there's no other question, I like to go back to the point you keep asking, maximum friction force, okay? Now, I think we already explained how they did the experiment. They don't lift the pad itself, they just lift the stick. And they measure when that is the force which lifts the stick. So that should qualify as a maximum frictional force, right? Static friction. Do you agree?
I think when they lift the stick and there is relative velocity between the vessel and the stick.
No. Of course, there's relative velocity. Otherwise, it won't be able to. But the definition of static friction, you keep driving at. I thought we should give a clear answer. Is it the maximum static friction?
I think they mentioned it in their experiment, but I don't think it is.
That's true. How do you do it?
I think the static friction is that they didn't have the relative motion between vessel and the rice. So for the maximum will be like when
it starts to move.
It starts to move. Yeah.
Right. Isn't that correct?
Well, we think that's
You think it's correct, right? But you don't. Reporters, of course,
Yes, I agree with
that's
that.
their idea. It's not important, but I thought for clarification, I thought you were on the same thing. Okay, your time is up.
Okay, so scoring time. Okay, so the score for the reporter. Six, 8, 7, 8, and 7. So the score for the opponent. 6, 7, 6, 7, and 6. And scores for the reviewer. Okay, 6, 8, 8, 7, and 7. Okay, so this.
Greetings, honorable judges and worthy opponents. I am the reporter from Team Waco Earthday, and today we will be setting off the agenda with problem number 15, pancake rotation. Again, to reiterate the agenda, we will start with our problem statement, then phenomenon that we observed, our observation, the theory that we used to conduct the entire phenomenon, the experiment that we conducted, and finally we will reach to our final conclusion. Again, to reiterate the problem statement, first we'll have to place a few balls in the round container, and if we were to move the container around a certain vertical axis, the balls inside the container could move co-directionally with the movement of the container, or they could move in an opposite direction. Henceforth, we are today here to explain this phenomenon and investigate how the direction of the movement depends on several relevant parameters. And our team believes that the debate's focus should be focuses on 3 points, including first to explain the phenomenon, second to investigate several relevant parameters, third and finally the most important point to determine the boundary condition. So our experiment setup is listed as above. So as you can see, we'll have a camera on the top observing the entire motion and recording the entire motion of the container and the ball. And for determining our container's RPM, we will have a orbital table down here. And it is important for us to know that our orbital table could only reaches a certain value of 230 revolution per minute. And we will have a data point where we would use tracker to track the entire motion. And the table's rotation direction is counterclockwise. So in regards to the phenomenon that we observed, as you can see, when there is relatively lower number of the marbles presented in a container, the marbles in the container actually moves within the rotation of the container, meaning that it moves co-directionally with the container. As such, in between the phase where the marbles moves rotationally and counter-rotationally, there exists a brief phase of stalling motion in which the balls basically just sticks to the container surface and do not move at all. And then we enter the phase of counter-rotation, where, as you can see, with more numbers of marbles present, we use tracker to track the motion of the balls, and you can see it is moving counter-directionally. And our theory will be mainly focusing on the stalling part and the counter-rotation part, as we do believe that the rotation part of this experiment is very hard to be defined, as various parameters may exert influence on this kind of movements. So, in order to for us to introduce our theoretical model, several assumptions must be made, and the accuracy behind these kind of assumptions would be further discussed later in my presentation. So first, one of the assumptions that we must make is that the assumption that we made is that the cluster of the ball could be concluded as a plate rotating in the container. And so several assumptions that we must make is that first, the period of the green point's rotation is the same to the period of the container's rotation. Secondly, the arrangement of the marble cluster do not change. Thirdly, the marbles in contact with the ball barely moves while counter-rotating, thus proving them to be in the same motion, and thus, henceforth, we could approximate the counter-rotating cluster as a plate. In regard to that, I will now introduce our theoretical model. So, our theoretical model is drawn as here. So, the uppercase R would be representing the radius of the container, and the lowercase r would be representing the radius of the plate. Point C would be representing the center point of the plate, and point K would be where we would use a different color for the tracker to measure the ball's motion. And with that, I will now introduce our theory, which is coin rotation paradox. So basically, if we were to use coin rotation paradox in this case, we could first initially find out point K's rotational angle relatively to point C when the plate finishes a rotation, to be the equation as above, which is uppercase r over lowercase r minus 1 times 2 pi, and the unit is in radian. And in regards to the first equation, we could then conclude the second equation. And before we do that, we're going to define several terms that we will be using in the later on presentation. So x would be defined as the container's rotating speed in the units of revolution per minute. Y would be accounting for the area proportion in percentage in regards to how much the marbles fill up the container. And lastly, value z in the units of radius per second would be representing point k's angular velocity. Thus, with that, from equation number 1, we could derive equation number 2, which stands for case angular velocity. And with that, we could further derive using the term that I just explained to this equation, which I will be using thoroughly through the presentation. And so, in regards to our first experiment, which is inclusive of the preliminary experiment, I will be explaining why our theoretical model is accurate, and I will be discussing the relationship between the number of marbles and the average angular velocity as a single particle. So we used basically image J to track the area proportion of the marble, and we used tracker to track the motion of the marble. So as we've seen in the tracker and several data analysis that we did, these 3 points that we selected these 3 points to be the point where we would determine whether the ball's arrangement changed. And in regards to that, the ball's arrangement almost remains constant while moving, meaning that say 0.123 would always remain 0.123 from most outer to most inner. And since we could conclude that same average angular velocity is exerted in every single position. And again, to reiterate, we will define the average angular velocity as 2 pi over the period of marble going around the container, and the unit as well is in radian per second. And the experiment number 1 is that we will keep constant RPM of our counter rotation, and we will be adding 2 marbles at a time into our container, and we will use tracker to measure the period of a marble going around the container, which is point K. And as we could conclude from the previous experiments, so first I just want to restate that for us, average angular velocity, as long as it remains positive, it will be meaning that the marbles is moving in a co-directional movement in relative to the container. And if it reaches 0, it will be confined in a stall movement. And if it reaches negative values, it will be moving in a counter-rotational movement. So thus, from our experiment, which we concluded like 10 times, thus the error bar is there as presented, we could show that initially when the x-axis represents the number of marbles that we added, and the y-axis represents the average angular velocity. So we can conclude that as the number of marble increases, the first motion that we will observe from the marbles is rotational movements, and second, we will enter a brief phase of stalling, then we will enter counter-rotation, and finally, when the area proportion reaches maximum, we will reach a stop motion. And experiment number 2, in regards to that, we will be discussing how the rotating speed actually affects the average angular velocity of the ball. And specifically in regards to the counter-rotation movement, as I mentioned before, we will only be discussing that in today's presentation. So basically, we will maintain the number of balls, or say the area proportion, as a constant, as a fixed constant in this case, and we will be changing the rotational speed of the container's rotation. And again, we will measure the period of the marble's rotation. And it is important for us to know that, so first in our experiment, we concluded that as area proportion goes over 94.1891%, it will enter counter-rotation. And as long as this number stays below 97%, it will remain in the counter-rotation movement and not exceed towards the stop movement. So from the equation that I concluded previously, we could get the pink line, which is the theoretical value, with the x-axis representing the RPM and the y-axis representing the average angular velocity. And with that, we put our experiment data in the trend, and we could totally tell that the data presented fits into the theoretical value because we actually performed a residual graph, which in statistics, when there is a scattered dot, it will be showing that our theoretical value matches with our experiment results. And thirdly, I will be defining the boundary condition, which is, as well, I believe, is really important for this case. We will be changing the acceleration we will accelerate the container's rotating speed, and we will record the number of marble it takes in order to make the cluster in this stall rotation. And we initially changed the container's area to see if that's a determining factor, and as you can see from the trend line, it is not. Instead, it is the area proportion that we should be focusing on in this debate. So as you can see, when the black line represents the stalling motion, and the red line represents the theoretical value. And the theoretical value actually varies because whenever there is a different RPM, the constants on this equation would vary, and hence we could conclude that as if we were to go above the stalling line, we will enter a counter-rotational movement, and if we were to go below, we will enter a rotational movement. And taking friction into consideration, we could tell that since the red line represents the theoretical value and the black line represents the experimental value, the yellow area right here represents the deviation caused by friction, no matter the static or kinetic energy, since it includes both spinning and rotational movements. And the blue area would be defined as where the counter-rotational movement happens. And then by such, I will reach my conclusion. So first, as area proportion increases, the movement changes from first rotation, then enters brief period of stalling period, then we will enter counter-rotation, in which the constant mostly remains the same. Then lastly, we will enter a stop motion once again. And there exists a directly proportional relationship between the average angular velocity and the counter-rotation. Average angular velocity in a counter-rotation movement between the RPM of the container. And lastly, our experiment results successfully proves our boundary condition to be set initially, henceforth proving our theoretical model to be right. And that will be it for my presentation. Thank you.
Question of the opponent to the reporter.
And is your container a steady rotate? Yes or no? Your container is steady.
What do you mean by steady rotate?
Oh, okay. And if
So you can't define steady rotate.
oh, maybe we discuss it later. And could you please turn to page 21? Oh, okay. And have you observed that the ball will move by itself?
What do you mean by the ball will move by itself?
Oh, for example, here you observe the ball will rotate like this, and have you observed that the ball will rotate like
As
this?
we mentioned, spinning is in consideration, which is why there exists a divergence.
And when you analyze the angular velocity, have you considered you consider all of the particle or one of the particle?
As we mentioned, point K is considered.
Oh, what do you mean?
Point K is one particle.
And does all the ball move with the particle cluster, or does all
As
of
we
them?
mentioned in our theoretical model, yes.
And friction force between the ball and particle will cause a rotation. What causes the ball rotation? Is friction force or what?
There exists both static and kinetic friction, which cause errors in the
And do you think a collision between balls exists?
that as well is considered as error graphs. Right over there, see? The yellow area.
So yellow area is collision. And do you think the density of a ball distributes in a container is the main reason that causes the reverse rotation?
We believe that the exact term should be area proportion instead of density.
Area proportion. And do you think the normal force from the wall to a ball is important? The normal force that's given by the wall to a ball.
As we mentioned, the marble barely moves when it comes to contact when the marble is coming to contact on the wall, so it shall be negligible.
Okay. And do you consider initial condition for a ball? That means your random put it in is random or not?
What do you mean by that?
For example, when you put the particle in
Okay, time's up. So preparation of opponent 3 minutes. Antonio, please take the floor.
And hello everyone, I'm Typt from Team ECN 1970. And today I'm going to opposing problem number 15, matrix rotation. And the problem statement said that we have to investigate what caused the co-directionally rotate for the particle. And I think we should mainly focus on explain the reason for reverse rotation and investigate the situation for clockwise rotation and reverse rotation. And how does the parameter affect angular velocity? For overview of report, actually they have shown us for experimental setup, and they have a rotational device which can control the container to rotate regularly. And they have described the phenomena like rotational and stalling and counter rotation, and the path check by checker. And for theory, they have counter rotational, and the mobile is in contrast. Some motion as the container see it a big cluster, and calling rotational paradigm. And it's related to rotation angle, angular velocity, container rotational speed, and area proportion. And for their experiment, they have changed the number of particles, and also they talk about rotate, and they also changed the rotational speed for the container, and they also explain what is boundary condition. And for conclusion, the number of the particle will affect both the rotation, reverse rotation, and stall. And since the rotation speed of the container becomes bigger, the relative angular velocity will decrease. And since the area increases and the movement of a ball is hard to rotate. And for some invention and suggestion, actually they explain the phenomena in detail, which they think for the counter rotation, stall, and rotation. And they explain the theory in detail for coin rotation, paradise, and counter rotation. And they quantitatively explain the experiment results, the relationship of the model and experimental data. For some suggestion, actually they don't show us what is the force diagram, and the big cluster should be considered only one force rotating in the container. So when it changes the number of the marble, it shouldn't see it as a big cluster to analyze it, because we have to investigate what's the collision between the both. And lack of explanation of the transition law. And lack of explanation why cause the deviation between the theoretical model and experimental data in their parameter for change the number of particles. And for some point to be discussed. And I think we will discuss about the observer, if it's in an inertial system or non-inertial system, and talk about what's the force analysis. And for some initial condition, for reporter, they didn't describe what's their initial condition. Have they have a regular distribute in the container, or they just randomly put it in and then start rotate. And the collision of a particle cluster. And for experiment, we will discuss about the three parameters that the reporter have done. And okay, let's move to a discussion part. And could you please turn to page 10? So I have asked you a question about what's the initial condition, right? So do you think that if you random put it in, or maybe here they will have a, for example, here first layer, second layer, or third layer. Do you think the initial condition will affect it?
First of all, you mentioned random, right?
Yes.
So where do you see first layer?
So you think
it's not?
Oh, so you already put it in is random. So you think the random won't affect the experimental result?
Of course.
Of course. And could you please go? Dr. Brentford. Thank you. Could you please draw the force diagram like here? Here is a container. So it has a center, and it will rotate around the object. And could you please draw the force over particle?
The exact reason why we chose not to do a force analysis is
And could you please draw force diagram?
Listen, the only reason that we did not include a force graph right here is because we believe that the force analysis right here would be too complicated to resolve. If you want to, you could draw it.
And, okay, I draw it. And here, maybe we need to discuss about here. Let's have two particle clusters because you didn't consider what is collision loss. So maybe if we need to draw a force diagram, here you use inertial system. And
where did we use inertial system?
I mean that because you are in an inertial system, so you can't draw a force diagram. But here, if we are in a non-inertial system,
Why are
we
we
can draw.
discussing inertia and non-inertia system?
I think the force analysis is important in your experiment because it will cause a normal force defect. And the normal force defect.
Could you please draw a collision?
Okay, I see it. And here, you have mentioned the friction. So could you please draw the direction of friction?
The direction of friction could also be random. Like as you said,
Yes.
the direction of the ball. Are you gonna let me explain?
Okay.
So as you said, the ball is put in a random order, right?
Yes.
So the collision, as you mentioned, of the ball would be randomized. So how can you determine the friction?
Maybe you can assume
So that's making assumption. That's making everything ideal.
Yes. So here we think.
But we are performing a real experiment, not making
So you
something
think you
ideal.
didn't need to consider one simple collision between two balls.
But even though if you consider collision, your experiment will
So
your
how do
theory
you
will
think
still
it
be
can
ideal.
already be a big capture?
As we mentioned, I don't know if it's in my theory. So basically, we consider several of the assumptions to be true in order for my theoretical for my theoretical model to be true. If you have clearly listened, there would be several points in regards to that.
Okay, I think a normal force is important. So could you please listen to me to explain it? Okay. And here you have a friction between the walls and the particle. So the friction is important because it will increase the.
We're not saying that friction is not important.
Okay, I know you said that friction is important.
So why are we mentioning it again?
Okay, now I'm talking about force drag. And here, they have a friction between the surface and the particle. And also you have a collision between, so we need to consider normal force between the two particles. And yes, about this. And okay, maybe we'll discuss about experimental part. And could you please turn to page?
Do you want to resume back here or do you
Okay.
want to stay?
Page 2.
Do you want to
Yes, thank you.
page?
2. Could you explain why the deviation in here is bigger? Why deviation in here is bigger?
This is called error bar. So
It's
basically,
called error bar. So I think maybe if you don't consider the collision, the rotation speed, the rotation angular velocity should be like this. But you don't. But you can.
do you want to let me explain?
Hmm?
Do you want to?
Yes.
So our experiment is conducted 20 times for every single point in regards to this. And in order to prove our error bar, so in order to draft our error bar, we included a 5% error, which is included in our experiment. We performed multiple times of the experiment, which is why error bar exists.
Okay, I know you have error bar. So could you explain why here the deviation is bigger and here is smaller? It will become bigger and then smaller. So could you
So
explain
as
the
you
reason?
said, the ball, the marbles inside the container is randomized.
Yes, so you can
So
say that it's random.
with smaller numbers of marbles, we will gain a more random results of where the marble, of the entire dispersion of the marble. So the marble is in a more random possibility. Do you agree with that? Are you agree with that? So if you were arguing with that, you would be saying that since they would be different, a lot of more different kind of like balls movements inside of this, this would cause the deviation to be higher. If that's
So
what
I think if you would like to describe why it causes deviation, you should consider what is collision. So why don't you consider collision between?
I am not disregarding collision. As we mentioned, there exist errors between our theoretical value and our experimental value, which is right here, the yellow area.
Yes. So could you? So it means the collision only exists when the angular velocity is.
Do you agree that collision causes friction?
Collision causes friction. You mean which friction?
Do you agree that when there is collision, there exists friction?
Which friction? You mean the friction between the two poles? Yes,
Yeah.
this exists.
It exists, right? So that's what I mentioned in my presentation. So these right here, the yellow area represents the deviation caused by friction, which includes the movement of collision as you kept on mentioning and mentioning over and over again. It's included right here. It is why our theoretical value does not perfectly match with our experimental value.
Okay, very good. And could you please turn to page 15? And how did you get a theoretical line? It's from which function?
Here.
Here. So how did you define y? You mean the y is a density, is a proportion.
Area
Proportion. So how did you calculate it?
we use image J.
You use image J to calculate y.
The area.
Could you explain it?
So area proportion is the area, the marble covered over the container's area,
Yes.
correct? And with that, we use imagery to analyze how area proportions should be determined. Okay?
Okay.
So in regards to that, we found out that in our experimental analysis, as long as the area proportion exceeds this value, and as long as it's under 97%,
Yes.
the entire movement of the ball inside the container would be in the counter-rotational movement.
Could you explain here the y is the angular velocity. So the angular velocity. So your analysis in the graph. So how did you analyze? So it's absolutely.
As you remember,
Yes.
the value x represents our RPM. So with
Yes.
that value and with the y value, which I mentioned in my presentation is fixed, we could get this one. As you can see, x is related to x, z is related to x, and y, z represents the angular velocity.
Okay, I got a point. And could you please turn to page 15, page 12 again? Could you explain why here it will become smaller? Why it will become smaller? It will keep reduced, right?
As we mentioned,
Yes.
so there exists. So basically, could you agree the fact that average angular velocity, when average angular velocity is positive, it's a rotational movement. The movement of the ball is the same as the movement of the container.
Yes,
Okay?
it moves the same.
Okay.
Yes.
And when it is negative, it moves counter-rotational.
Yes.
So the,
Why did you decrease?
so listen. So the question mentioned that we will turn from a rotational movement to a counter-rotational movement. So in order for the experiment result to show that, we'll have to start from a larger, which is a positive number, to decrease all the way down to the negative part so that we can reach counter-rotation. This is why it decreases. And it will not increase because if it increases, it will still remain a rotational movement, which is not in the phenomenon that we observed, nor is it in the theory.
And why do you choose minima? It's 52. If you keep doing the experiment to 0, and what will be the result?
Say if there's one marble inside the container. And if you rotate it, the
Yes.
marble will still be remaining in
So it was the steady rotational motion. So will it be a constant or it will be like this?
We believe that there will be a linear graph going up there.
Yes. So it has a limitation. So you didn't consider what is the limitation for rotational.
So basically,
Oh, I mean when you change the number of a particle in the
no.
experiment.
We did consider that. See, and
Yes.
this is the entirety of our limiting condition in which the phenomenon will be observed. So
And
you can
here
use the
the
rotation.
angular velocity is not a particle. The number
Angular
of
velocity is related to the RPM of our container because of this equation. If you clearly visited our equation as proposed in a theoretical model, you could be able to do simple math and conclude the fact that RPM is directly related to the angular velocity.
You mean that RPM related to which one?
Look at this.
I mean when
Look at this.
yes.
C represents angular velocity. X represents RPM. So if we have X, we have Y, we could get Z.
So you calculate what these the angular velocity of particle clusters.
Yes.
Yes. Okay. And so how do you get a theoretical value?
Again, as we mentioned, the limitation of our RPM is at 230 revolutions per minute. And again, if we were to implement that value inside this equation, we will get a theoretical value in which our Z would only range from 0 to 0.8.
And could you please specify 21? And 22. Oh no, maybe 19. Oh, sorry, that's crazy. So here, what's it mean?
So basically, right here in this experiment, we are trying to explain if, like, the area
And
influence.
could you please explain why here will be the same?
The trend line is actually the same.
Okay,
You
time's
mean
up. So the opponent summarize the discussion.
And I think I have discussed about non-inertial system. And for our opinion, I think the reason that we need to standing in the system for a non-inertial system is important because we can see the counter rotation in the inertial system. And because when the density of a ball is too big and it will stop. So when it stops, however, when the observer is in a container, the motion of a stall and reverse rotation could be seen. And for force analysis, I think we need to consider, if we are in a non-inertial system, we need to consider centrifugal force, friction force, normal force, and the collision between the balls. And the collision between the balls is important, and it is the reason what causes the ball's reverse rotation. And for collision force, and the normal force and the friction force between the balls would affect the direction how the balls move. So if seeing multiple balls as a big cluster, then the parameter of a changing balls number will be necessary in reporter's problem. But in fact, the detailed interaction between the balls and two balls will affect different motion.
Okay, time is up.
Thank you for your attention.
Question of the reviewer to the reporter and the opponent.
So first of all, I'd like to ask both of you guys, where do you think the energy from the counter rotation comes from?
It obviously comes from the RPM of the container.
I think it is from friction types.
And second, so when the number of balls in the container is sufficient, is there a complete stop?
Can you please explain it again?
Are you directing to both of us or?
Both, you first.
Can you define sufficient?
Sufficient, so like
Like
your
numerically sufficient, what is it?
in your graph, when you put your balls, like in 72, you define the phenomenon as stop.
Yes,
so,
this is an experimental phenomenon.
So do you think there is a complete stop?
Complete stall in the ball? Yes, when after it reaches the counter rotation, and when the area proportion exceeds 97%, as I mentioned, it will enter a stop motion.
And yours?
Do you mean the particle in the rotation of the ball? Rotation of a ball. You mean the amount of air becomes
When the balls becomes sufficient, do you think there is a complete stop?
Yes, it will stop.
And next, which friction? You first. Which friction do you think that the balls experience to allow
Both
it?
static and kinetic, owing to the fact that
Which
the ball,
friction did the beast experience to allow it to move as if it were a solid plate?
again, to reiterate, we're not neglecting friction. We taken into consideration of both
No,
static
I'm not
and
stating
kinetic.
that you're
Static
neglecting it.
and kinetic.
Which friction do you consider to move as a solid plate?
Static and kinetic.
Solid. So which friction?
I think it's a kinetic friction between a container surface to a particle.
You first. In general, the counter rotation velocity is stable. Yes or no?
Counter rotation velocity is stable. It depends on
yes or no?
It depends on the amount of balls.
And
It is stable.
that's it. Thank you.
Thank you.
The declaration of the reviewer, 2 minutes. Okay, reviewer, please take the floor.
Reservists and fellow competitors. I'm Tyler from 18 New Gates, and this is our review for problem no 15, basic rotation. So the problem statement is that you put rotation paradox. For experimental factors, they stated that the number of marbles affect the most, and also the rotating speed. In conclusion, the origin was constant throughout the experiment. Rotation speed increased, related angular velocity decreased, and area cover increased. Rotation was installed to constant rotation. And for the reported presentation, and they have videos, error bars, and they use theoretical volume to carry out their experiment and answer the essential questions. But we think that they could be more parameters and materials though. For opponent, they ask questions from lots of parameters and look at the presentations, reporter's presentation in detail. But there are some missed points for the reporter's presentation and focus on points not included in the reporter's presentation. For the discussion, the first question is, if you put it in randomly, will it affect? And the answer from the reporter is yes. Please demonstrate the force. And the reporter replied, it's too complicated, which is the reason why it's not included. Why is it division here bigger? Because it performed experiment many times to draw the error ball. Is collision taken into account? And yes, the yellow area is a deviation caused by the friction of the collision. How did you get a theoretical volume? By formula. What will happen if the number of marbles are over 50? And they believe that it will be, the phenomenon will be linear. Questions for reviewer. Where does the energy come from? And the reporter stated it's from RPM, and the opponent stated it's from friction. And our opinion is that both should be considered. Our question is, will it be a complete stop? The reporter stated yes, and the opponent said yes. And yes, the energy loss from friction causes all energy to be lost. What friction does a piece experience to allow it to move as a solid fits? So the answer from the reporter stated is static and kinetic, and the opponent is kinetic. Next is a counter rotation velocity signal. The reporter said it depends, and opponent yes. Our opinion depends on number of holes. And that's it for our presentation. Thank you.
Concluding remark of the reporter.
Greetings all. I would like to first appreciate the jury's attention and the participation of both the opponent and the reviewer, and hence I will be starting my concluding remarks. Again, to reiterate, we did not include a force analysis graph because our theoretical model is based on a plate, which we do not think force graph would be necessary. But for further improvement, if we were to consider the entire experiment all over again, we could consider it not to be a plate, but to consider the force graph of each model. And to clarify, the precondition and the boundary condition of our theoretical model was clearly presented in our report, with the yellow area, as you guys remember, representing the errors that might be presenting, such as the friction, the collision, and all sorts. Vast number of experiments, which is like basically over the 20, was conducted in our topic to fit our theoretical model, and it is explained over and over again to the opponent and the reviewer. And that set forth, there are clear phase distinctions that were presented to clarify the phenomenon and the accuracy of our theoretical model. And lastly, we do include a lot of different parameters, such as the area of propulsion, revolution per minute, and other factors that our experiment have conducted. We could probably say that our theoretical model, without force analysis, fits the reality of the phenomenon. And this will be the end of my concluding remarks. Thank you.
Okay, so questions by the jury?
I have a question for reporter. Could you turn to your page 12?
Oh, yeah, okay, hold on. Page 12.
Yes. Actually, my question is the same as your opponent. Could you explain why the rotation keeps on decreasing when you increase the number of holes?
Okay, so for us to more clearly clarify this, we do believe that we talked about something, but so basically what we set the theoretical value to be is that average angular velocity is when average angular velocity is positive, the ball's movement inside the container would be the same as the container's movement, meaning that it will rotate rotationally. And when it reaches when the average angular velocity reaches 0, we would be seeing a stalling motion, which means that the balls would be confined. It's really brief, but it exists. And lastly, we will reach the second phase, which is counter-rotation, as the question stated. So we noticed that as the amount of so basically the negative value of average angular velocity indicates that it is in a counter-rotation phase. So in order to go from a rotational phase to counter-rotational phase, we will need to gradually decrease till the value reaches a negative value.
Why it doesn't look like a straight line and suddenly become like this?
Oh, because we believe that there exists a stalling phase, because in our experiment we did observe when the number of marbles in the container reaches 61 and 62, when the container moves, the balls doesn't really move, it would be
I understand, but why? I mean, could you explain why your data doesn't detect a straight line and suddenly goes to the next? I mean, why the data doesn't look like a straight line and then suddenly? Why do
because the area proportion increase in this case, making more and more balls all clustered together. So they're the increasing number of balls actually they cannot have that large of an average angular velocity because the amount of ball increases.
May I explain this diagram?
okay.
Thank you. That is purple.
Okay.
And here is a puzzle reporters. Here is a puzzle reporters diagram. Here is
But to clarify, this is not
here is
theory.
zero.
This is
So here it will be a constant. Oh no. Here is reporters. Here is reporters diagram. Here is 50. So if she keeps doing the experiment, she will find that here is a rotational motion, and here will be a transition. So yes. So that's the reason why it was.
Any further questions from the jury?
Could you explain where you use this model, paradox?
The model is
You use it to explain what? The counter rotation
and the stalling motion.
and the what?
Stalling, yes.
Okay, but not the ball.
The rotation part is included in the last where we set our boundary condition.
Excuse me?
The rotation part is included in the last experiment in which we.
No, I mean model. You don't that part. You don't use this model.
No.
Why?
Because so we believe that rotation, when a ball inside a container, when it's in a rotational movement,
But it's not like a disk because it's loosely distributed.
yes, because a lot of factor into it.
Okay. The reason the angular velocity decrease can it be attributed to the fact that you have more balls, and so you may think it is that the moment of inertia is increasing. Where moment of inertia times angular velocity is equal to I omega is angular momentum, which is provided by the collision with the wall.
So we believe that I times omega, which is the angular momentum, should remain constant in the rotational movement. So with that, with an increasing ball, we'll have.
You cannot keep how do you keep the angular momentum constant? If the wall if the ball keeps colliding with the wall of the turntable.
That's actually one of like our assumptions, which is that the marbles in contact with the wall barely moves. So basically, when it barely moves, it remains like the same ratio. Like the balls that come in contact with the wall of the container remain in contact.
And that's when you have many balls.
Okay, so now it is scoring time. The score for the reporter. Seven, 8, 6, 9, and 7. The score for the opponents. 8, 7, 9, 7, and 6. And the scores for the reviewer. 6, 7, 7, 7, and 6. Alright, so thank you for your participation.